Swayam Prabha. Digital India. Educated India.
Welcome you to this fluid mechanics class on fluid kinematics. This is second lectures on fluid kinematics. This is what quite interesting lectures what today I will cover it with starting from the derivations of vorticity to show the real time the vortex formations in Bay of Bengal, which is super cyclones what's happening today. So, let us have these lectures which started from very basics, how the vorticity is there and how the fluid rotations we are talking about that, and where very larger scales is mesoscale process of cyclones which can look like a vortex process, a very real time, near real times vortex formations what is available in internet what I am going to show you. So, this is quite interesting lectures for you to look at the vortex from smaller scale to the bigger scale. Today I will cover again these three books, and mostly I will talk about the recently we are talking about more Radhakrishnan's book and Sinjal Simbala. So, it is a good book on fluid kinematic. Now, let us have the contents of the today lectures. I will very interestingly I will show the experimental facilities what is there in Department of Chemical Engineering IIT Guwahati, particle imaging velocity meter which measures three-dimensional velocity components. So, when you measure the three-dimensional velocity component, then you can understand how vortex formations happens, how the turbulence characteristics happens. So, which is more important today's world to know it very micro scales the process understanding as compared to macro scales or gross characteristic things what we did it in 20 years back or 30 years back. Then again another examples from the as a CFD solvers, the collapse of water columns with obstacles, that what very interesting free surface flow, that is what we will see it. Then we will go for already I discussed about the Lagrangians and earlier descriptions. I will just touch upon that showing these the flow patterns what we are getting it. Then we will go for how the motion and deformations of the fluid elements, vorticity and rotational, and some few examples best for the motion and deformations, and followed by the summary. Now, if you look at the facilities what you have granted from the Department of Science and Technology, Government of India, this facility is known as the particle image velocity meter. So, where this is a facility which generates the laser beam, okay. So, and that laser beam pass through the test sections which has a two cameras, two monitors, how the laser beams are changing it. With a image processing, we can compute the three-dimensional velocity fields. I am not going more detail how we, what is the basic principle of particle image velocity meters, but there is instrument like a laser beams, then the test sections and the two cameras. Based on that, with these principles what we have given here to monitor the particles at different time frames, we can obtain the three-dimensional the velocity fields. As you see, it is very interesting photographs what we are coming from experimental data, because here you can get three-dimensional velocity fields. If you look at that, the two vortex are forming just from a pump exit, and the You can see these vectors, you can see the vortex shadings which is going down, and two pair of vortexes formations are there. And so these quite interesting figures of vortex formations and the propagations of vortex pair, that what we can go at it very detailed way if you have a facility like PIV or particle image velocity meter. So these very unique facilities, that's what we have in the Department of Chemical Engineering, IIT Guwahati. So, but what I am to tell it, at present we have the facilities to measure the three-dimensional the velocity fields very accurately, so that we can represent like this type of vortex process what it happens it. That can be possible it. Now let us go to the one of very interesting again from the acknowledging Professor Dalal and students group in Department of Mechanical Engineering IIT Guwahati, who has developed indigenous CFD solvers. Now if you look at this free surface, you can see that how interesting things are happening here. You just see this collapse of a water column with the obstacles. That means you have water columns that maybe have a water tanks is collapsing it, then there is obstacles. How the flow patterns happens, if you look at this free surface, it's very interesting things what is happening. And this the CFD solvers today it's able to capture these so complex process. If you look at how the complex process are happening it, how the mixing of water and air is happening it. So if you look at that, these are things it's really possible today now, it's not that difficult. And this is what is showing with a comparisons with the velocity fields and all with the experimental data sets. So if you look at this way, there are very complex processes also we can get the streamline patterns, velocity pattern, the pressure pattern, the free surface variations patterns, either using CFD solvers or having a experimental facility with particle image velocity meter. So if you have that, you can get the solutions that so complex solutions also we can get it, and we can see how the pressure variability is there, how the velocity variability is there, how the density varies there. And these the problems where there is a mixing of, there are two domain problems. This is the water is there, also air is there. So how these two mixings are happening, and that's what the complexity of the problems, and which is at present is possible to do this type of the studies, and which will give a very interesting thing. Let us come back to our basic fluid mechanics. Okay. So as in the last class I talk about two types of descriptions. One is Eulerian frame of descriptions, another is Lagrangian frame of descriptions. And that the descriptions we try to visualize as form of virtual fluid balls. Okay. So today I will talk about that I have the fluid element, which is in any of fluid mechanics book they talk about the fluid element, which is representing a certain space of the fluid particles, which is much larger scale than the molecules levels, or it's not that bigger scale to represent the flow process. So the mostly I will talk about which is called is virtual fluid balls. Okay. So when you have a balls, then it can go through any type of motions and the deformations, like it can be translations, like very easy that you have a ball, it can translate it, it can go in a u direction or v direction, or it can have a displacement in a x direction, y direction, z direction, and the displacement is caused because of the velocity component. So that means if the virtual ball, it's at a t time, and this is a t plus delta t time, we will have more detailed discussion how much it will travel it. That depends upon the velocity at the time t, and after delta t what could be the displacement, which is simple things, the displacement is equal to velocity into delta t. So it's very easy concept that how much of displacements will be there, how much of translations will be there. And the particle, the virtual fluid balls or the element, the fluid elements can go for a rotations. That means there is no translations motions. That means it's just go for a rotations. It's there only. It goes for either clockwise rotations or the anti-clockwise rotations. So the fluid element can go for a rotations. So that means we can compute what could be this angular velocity if it is going through a rotations, the clockwise rotations or anti-clockwise rotations. So if you try to understand that these rotations all it depends upon the velocity fields. The velocity field, the variations will cause the rotations of these fluid particles. The velocity of the field also talk about how the translations motions will happen from point A to point B as fluid particles are changing at the time t to t plus delta t. So, all it depends upon the velocity fields. So, that way we can have a translations or the rotations which is motions part. Then we talk about this fluid element as in the solid, it could have the deformations, like it can have a linear deformations, like it can be elongated. So, that means if you give a just stretch, okay, or you compress it. So, that means the elemental size, the volume of the fluid element that may increase it or can decrease it. That depends upon also the velocity distributions how we have. That what will be stretch the fluid elements or the compress the fluid element. Or if I have a virtual balls, so the basically the dimensions of balls will change it. See, if I have a virtual ball concept, that means what I am talking about that the dimensions of the ball can change it. Okay, if I have give a linear strain, okay, positive strain, it can expand it. If I give the compressing it, then it will be reduce the size. The similar way we can have a shear strain. We can have the shear strain to the fluid particles, like you can have the shear strains to the fluid. So, there is a difference between the rotations and the shear strains. Okay, you can see the graphical how they are the different. Okay, we will discuss more. So, the basically if you look at that, the fluid can go through two type of motions, translations and rotations. Also, it can have a deformations of linear strains and the shear strain. Now, come to the translations, which is very easy concept, okay, which is the velocity vector which is responsible for shifting a fluid particles from A locations to B locations. It depends upon the velocity components. Like in this case, you have a small u, v and w is a scalar velocity component in x, y, z directions respectively. So, that means at the delta t time, after the delta t times, these particles which is there, it can move it at a displacement of u into delta t, v into delta t, w into delta t. So, that way it will move in these three directions to get a new positions vectors. So, it is a simply translations from A point to the B point with by the velocity vector components. Okay. That means, these particles has the velocity vector component u, v, w, and at the t time at t plus delta t time, it will move it with a in the x directions you will be u delta t and v delta t and omega delta t from these origins locations. So, it is a very simple thing as you know it in solid mechanics. Okay. If a particles are moving with a u, v, w, what could be the display positions vectors at t plus delta t time. So, it is very easy, we can have that ones. Okay. But many of the times we see the one dimensional components, other components you may consider it is a 0. Now, coming to the rate of rotations, which is called angular velocity. Okay. What could be the angular velocity of the fluid element? See, if I take this is the fluid element, okay, it will have the velocity variations. That means, if this the u velocity is here, at this point you will have a u plus del u by del x into delta x as the x direction is changed. If this is the v velocity here, at this point you will have a v flow delta v by delta y into del y. What I am telling it, if I have a u and v, it is a two-dimensional element what we have considered, it is easy to understand it, and it is the z direction which is a perpendicular to this surface. So, that way it will have a rotations along the z directions, perpendicular to z directions, it will have a rotation in on x y plane. So, if I have a u and v velocity at this point, I will have a velocity at this point, it will be u plus delta u, if this is the delta x. So, delta u by delta x by into del. So, similar way at this point I will have the velocity the v delta v by delta y and del y, but the velocity, this will be the u velocity. So, similar way I can write the what could be the velocity at this point. So, now if you look at when you take a fluid element in the 4 corner points, we have the velocity variation because of this velocity component. Okay, because of this velocity component and this velocity component, the fluid particles is going to rotate it. Is it correct? The velocity component of the v at these locations, that what will be try to rotate it. The velocity component v u, the gradient, the relative difference of velocity component will be move it. So, that way what we can have, that how we can compute the relative velocity difference between these point, that what multiply with the dt will give a distance, and then we can get it what will be the angular rotations. Very simple way. If you want to have very detailed derivations, writing from the Taylor series, find out the distance travels, that computing all these component of the velocity at each points, you can follow any of my wave lectures which is there in NPTELs. So, but let us not I spend more time on that, let me leave very concept wise that the angular rotations, the rate of rotation of the fluid element about the point phi will be the half of the angle alpha a and alpha b, which we can easily write in terms of the partial derivative of v and the u component, the scalar component of the velocity. It can be easily written it if you follow the Taylor series and with these things. Okay. This is what that means, this is the angle of rotations is given a functions of in terms of the scalar, the partial derivatives of the scalar component of v and u in a x and y directions respectively. But if you want to make it 3 dimensionals, like if you look at these fluid particles, okay, I just computed for the z directions. Okay. Similar way I can find out what could be the rotations in the x directions and the y directions. That what will come it the similar like this. So, this is what the rate of rotations factors. It has x component rotations, the y component rotations and z component. This is a complete rotations factors is in terms of the change of the velocity gradient in x, y, z directions. So, that so please try to have a simple relationship to try to know it. Whenever you are getting the compute the rotations in the y z plane, you need to have a scalar gradient component in x and y. Similar way, if you want to have this computing these rotations in the ith plane, that means you are looking at the scalar gradient of z and the y plane. So, those things you can just remember it, or it is not necessarily you try to simplify it as get a fluid elements and you just think it. But if you come to the virtual ball concept, the same concept I can tell it, there will be virtual ball concept. What I am talking about now, that not the fluid elements, it is a virtual fluid balls. That means there will be a series of balls will be there. Since there is a velocity gradients are there, so these balls will try to move these directions, these balls are try to move to these directions. Because of that, there will be start a rotation. The direction can change it, they can have a clockwise direction. So, basically if you think it, there are the balls are there, as they have the different the velocity gradients are there. So, they will move different displacement. As a jointly we can see there is a rotations what is happening it. As a rotations what is happening in a z plane, as well as we can compute for x and y directions. Now, coming to the very simple thing is called linear strain rate. That means, what is that strain rate? Rate of increase the length per unit length. This is very simple definition. Okay. So, rate of increase in length per unit length. That means, let you have initially you have the fluid element which is starting from P to Q. Okay. At the point P you have the velocity u alpha, but at the Q we should have based on the Taylor series you can have this velocity. At the delta t times, this P point will move to P dash, the Q point will move to Q dash. The distance between these two will be different. So, that is the reasons there will be a linear strain. Distance travelled by these P and Q will be the different, as the velocities are the different at the P and Q. If the velocity difference between the P, Q not there, then we may not have a linear strain, will not have a linear strain. Since there is a velocity variations, the fluid element which connected as a virtual fluid balls from P to Q, Q moves more as compared to the P. So, you have a stretching of virtual fluid balls, stretching of the virtual fluid ball. That means, they will stretch it, they will be the same dimensions, but they will be stretching it. So, they will be elongated as the width will be reduced, the length will be changed. So, you have this part. So, increasing length of PQ like the seg, which is else a positive linear thing. When a flow is incompressible, the net volume of fluid element must to remain constant. If the fluid is incompressible, that means the density does not change within the fluid flow domain. It means that the net volume of the fluid must be constant. Now, if you look at these problems that, so you can find out this linear strain rate is very easily, that linear strain rate length you know it, divide by this per unit increasing length you know it, divide by this the original length, we will get it from that what will be the linear strain rate. So, we can compute it what would be, that is why we can easily compute it what will be linear strain rate, which is the gradient of the linear strain rate in the x directions, the y directions and the z direction. If I am looking for a volumetric strain rate, that means will be sum of these strain rate what we are looking at. Let me have a very simple examples, how you have like you have this type of flow, the conduits are you have. When a fluid particles is coming like this or virtual balls is coming it has the velocity variation. As soon as it comes here, it has to be bigger size. So, it have to occupy this space, it will have this. So, these fluid particles from this point to A and to B, when passing through, it has gone through CH strain deformations. So, if you look at these fluid flow problems, which is very easy things, that there is a smaller diameter pipe, it is connected to a bigger diameter pipe. When a fluid element is coming from this point, as goes to this point has to be increased, there will be a linear strain rate what is going to happen in this case. So, because of that there will be reductions of width. So, if we look at this way, whenever a fluid particle is passing through a smaller to bigger dimensions or bigger to smaller dimension, it goes through a strain rate formations. Now, if you look at, if I look at a volumetric strain rate is a sum of the shear strain rate in the x, y and z directions. As you know it, for incompressible flow, the volumetric strain rate becomes 0. That means, what is this? Is a dot product of delta and V is equal to the 0. So, this becomes a conservation equations, the mass conservation equation for us if you consider the flow is incompressible. Now, let us go for the shear strain rate. What is this? The shear strain rate is a half rate of decrease of angle between two initially perpendicular lines that intersect at the point. What it is saying that if you look at these figures, that I have a figure like this, the fluid element at the T1 time, at the fluid element at the T2 time. At the T2 time, this line is moving alpha and alpha A minus B angles. So, we are looking at half of that angles, the decrease of angle between two. That means, because of shear strain rate, you can identify the edge and how these edge are changing it. Okay. On average, how much of edge it is changing it with a two perpendicular lines. Okay. You can understand it if I have the shear stress is acting it, the strain will be the angular rotations, and since it is a fluid element, we will have to have a two axis, and with that two axis formations we are looking at that what is the angle rate of the change of decrease of angle between two initially perpendicular line, that what intersected that. So, again you can find out what will be the shear strain rate with the half of this change in the alpha minus AV. Okay, that angle between these two change, that what again you can estimate it and you will find out the linear shear strain rate will be functions of u and v, the scalar velocity components, the partial gradient component, what you will get it is function like this. So, you can easily understand it that if I have the fluid particle balls, also can find out how much of rotations are happening it, and because of if in case of angular rotations, both the axes are rotating in the same rate, but in this case the rotation rate are the different. Because of that, you can see that deformations, the fluid element deformations. So, as of now what we have done it, we can get a shear strain rate in a Cartesian coordinate for different plane, xy plane, zx plane and yx plane, and finally we can write the shear strain rate tensor, which will be linear strain formations and the formations of shear strain rate. So, it has a 9 component of stress strain rate tensors. Okay. So, you can find out the strain rate tensor functions which will have a 9 components. So, if you look at that, the strain rate tensors is a functions of partial derivative of the u, v, w scalar velocity components. There could be positive, there could be the linear part, but they are all depends upon the velocity variations in x and y z of planes. So, how would they velocity variation, and that velocity variation causing us the shear strain tensors. So, as you know from the fluid mechanics or the solid mechanics, stress is proportional to the shear strain rate. So, we can easily establish the stress and the shear strain rate tensor functions very easily if you know the shear strain strain rate tensors. But in these 20 hours lectures, I am not going more details about these functions, because it is limited to this way to just describe you how the shear strain rate functions are there. So, let us look at another component is called the vorticity or the rotationality. When you talk about a vorticity vectors, basically we are representing as a vorticity vectors, which actually the measures of rotations of a fluid particle, which if you can look at the rotations of fluid particles can be twice of the angular velocity. So, it is the curl of V, okay, and half of the curl of the V is, as you know it, is angular rotations. You just substitute the V functions and do the cross products, you will get the divide by 2, you will get the rate of rotations, or indirectly that it has a relationship with a vorticity with the rotations, because this is what again a representation. Vorticity factors, if I know the cross product of the delta and the V, it is 0, then we can say that the vorticity is 0. That means there is no rotations, there is no angular rotations. Like for example, if you look at very interesting photographs figures, okay, which is modified from Sinjal-Simbala books. I think you please remember these figures, okay, with very interesting figures for a fluid mechanics student point of view, that when you have a flow passing over the plate, you can anticipate it that you will have a viscous effect zone, which is called boundary layer formations. There is a zone where there is large gradient of velocity factors. The velocity will start from 0 to a large gradient will be there. Since there is a large gradient of velocity variation is there, as I said it earlier, that velocity vector change from one point to other point. So, the fluid particles will not go straight line, they will start rotating it. So, that way this figure is rotating that when the fluid particles enter here, there are large velocity gradients are there, the turbulence is there. So, the boundary layer formations are the zone where viscous effect dominates. Okay. Those regions you will see their vorticity will be there, or you just have the cross product of the del and the V will show the vorticity, and graphically you can see this phase of these ones. Okay. It is just a vorticity. Okay. It is a rotations. The fluid particles will go under the rotations, but just a particles which is much above this, okay, where there is no vortex, you can see the phase of these ones. Okay. They are just same, there are no rotations. So, then we tell it irrotational zone. This is the outside of the boundary layers. You can see that fluid particles are moving it, or the virtual fluid balls are moving it without any rotations. But within the boundary layer formations, the small regions near to a surface, you will see there is a change of the velocity gradients, the drastic change of the velocity gradient, and those are regions, thin regions which called boundary layer. There, because there is large, the variations of velocity factors induces the fluid particles to start rotating it. Once you start rotating it, so once particles start rotating, other one will start rotating. So, all the particles start rotating it, and that what is having formations of eddies formations and all, which we will discuss in the later on in a pipe flow chapters. But you try to understand it like these figures, you please try to visualize these figures and see there will be the regions where the rotations will be very dominant, and there is a regions you will not have a rotations that much of a dominant. It can consider is irrotational zones where the fluid particles will not go for any rotationals. There will have the translations, there may have the shear strain formations may have the linear strain formations, but they will not have a rotational activity. So, that what we measure in terms of vorticity. So, please do not have a very confusions between the vorticity and angular vector, because vorticity is easy to define, is a cross product between the delta and the V, where each when you talk about angular rotations, we have half of that. So, it is very easy, people who are not looking the angular rotations, they are looking it in terms of how the vorticity is playing it or vortex formations happening it, they talk about at the vorticity level, not at the rotations level. These are very examples, as I said it, that when the fluid particles outside the boundary layer has a geovorticity non-rotational zone, but inside the boundary layers it will be a non-zero vorticity. So, flow is irrotational. Air is still surrounding the irrotational, but it is obstructed by object or these things. So, air flow wherever is that, if there is no obstructions, so it will be the irrotational. But when you start putting obstructions like any cylindrical type of subject, so you will see that very close to these regions we will have a lot of the rotational activities. But the outside, these are irrotational zone. Irrotational zone. So, you try to understand it, how is the formations, and this is the formations which is called the boundary layers and the wake formations. It happens for flow through the turbomasonry, the wake formations and all, and which causes viscosity, temperature gradient and the non-uniform phenomenon. Now, in terms of vorticity vector coordinates, if I put it in a ij k, I will have this component. If I am looking at two-dimensional flow, the flow does not have the z component, okay, and u and v are independent to z, then I have only one component. So, many of the flow, you know it, we can define in terms of two-dimensional flow. It is easy to visualize, easy to understand it, okay, as compared to the three-dimensional flow. So, that is what we can see. The vorticities can define in terms of the scalar velocity gradient component, partial gradient component in x and y directions, and the k indicating the directions where the vorticity directions, the z directions. So, vorticity vectors also can written in terms of polar and cylindrical coordinate systems for three dimensionals and also the two dimensionals. So, those are interested in high level of fluid mechanics, please look it the similar way, but derivations will change it, because there is r u theta 1 by r, the theta z r, okay, there are three different components, axis is there, and based on that we write the vorticity component. Now, if you look at these figures, you can understand it, which is irrotational, which is a rotational, okay, and the figures which is there in here, you can look it which is a rotational, which is a irrotational, okay. Because of that, you enjoy this the wheel, okay, because of it is a irrotational circular flow. So, you just sit it, you enjoy it because it is irrotational, but this is the rotational circular flow. So, that is what it happens in, and these figures what is there, very interesting figures drawn by my students, and you can really visualize these figures, and I do believe it, if you visualize these figures, you will never forget what is difference between irrotational and rotational flow. So, with this I can start solving the two example problems and conclude today's lectures. So, if you look at the first point, that I am looking there is a two-dimensional velocity field, state whether the flow is steady, irrotational, and check whether the given field is feasible. That means whether the mass conservation happens or not, okay. Or the flow is incompressible and mass conservation principles hold good. Then we are talking about the stream functions, and determining the volume flow rate passing through between the streamline passing through these 2 points. Okay. Even if I have not discussed about the stream function, but I will just introduce you what is the stream functions, and based on that you can always think how to get it the stream functions variability. Now, the flow is steady because you can easily locate this u and v component does not have any time component. So, the steady flow is irrotational, you can find out the velocity gradients and find out the flow is irrotational, and from the continuity equations or the linear volumetric strain rate functions you can find substitute these values, you will see that is equal to 0. That means the flow field is possible one. Now, coming back to the stream functions, what we define it. Okay. If you remember it, if these are my stream functions which varies in x and y, I am talking about the steady streamlines. Okay. X and y directions. As you know it, the stream functions change in the x directions, okay, should be equal to minus Vy, and stream function changing in y direction should be equal to the Vx. This what you can physically interpret it without having this thing, that the tangential component of the velocity vector, that what represent us these functions. So, considering this, the definitions of the stream functions, you can establish this is what the functions behavior relationship between the stream functions gradient and all. So, if as this function is 2 independent variable, we can define like this, substituting this value we get a stream functions. As you know the stream functions, you can find out the discharge between them, which is the difference on that, and substitute it here, you will get a 12 units. Please, I can encourage you to read more on the stream functions and all. Similar type of questions comes in GATE or engineering service. Now, coming to second example, which is a too easy example as compared to the first one, which is a GATE 2018 civil engineering questions, where u, v, w components are given it. Okay. Compute the z component of angular velocity at the point. So, the point is also given, the x, y, z coordinates is given it. You have to find out the z component of velocity, angular velocity. That is again the sketch of these figures, which is giving alpha and alpha b. You can find u, v, w. Then you know this relationship between these things, and you just substitute it, you will get it, which value which comes out to 3/2. So, the basically you try to understand it, you find out the scalar components, differentiate the scalar partial differentiations, you do it with respect to y, x or y, then you just substitute it, then you can get what will be the angular rotations in the z directions, which is here, and after that you substitute the coordinate x, y and y, z at that point, then you will get what will be that. So, with this let us start these figures. If you can look it, and as I said, it is very real time. Today is 3rd May 2019, and today is the cyclone is passing through the state of Odisha, and you can see this big vortex, how it is moving it, and how the velocity vectors, the vortex is moving it, and how it is causing extreme rainfall events, and how it has make it almost the coastal belt is standstill, no flights are running, no trains are running it. So, these are all it is a possibles now because of the high level of fluid mechanics softwares we have, and which is running at different levels to predict the wind velocities, predict the vorticities, predict all this process. You can really see it, and also predict the surge height. All it is possibles now because of our in-depth knowledge of the fluid mechanics, the use of computational fluid dynamics, and that is the reason it is easy for us to predict the flood or predict the cyclones at the accuracy of It's just 1 hour's difference of accuracy. We can predict at what time it will commit, where it will commit. So all these are possible because of our knowledge of fluid mechanics and because of our capability to simulate it. The very complex fluid flow problems in a big area, like if you look at what could be the large area at the global scale, also it's possible to predict it, and that's what today we are able to predict the cyclones even if a accuracy of less than half an hour. So we can exactly tell it at what time it is going to commit where. So it is all possible, and how will be the wind velocity and what will be the wind directions, all we can get a path of the cyclone tracks and all. These are all possible because of our knowledge of fluid mechanics and our knowledge how to solve these complex fluid flow problems using computer algorithms or CFD solver. With this, let me conclude it. These are all the summary which is listing all your equations. So, just have a really it's a good lectures to look at this vorticity. It's a smaller scale to the bigger scale with the cyclonic patterns. With this, let's have a give you a thankful for this lecture. Thank you.